So in last video, we proved this theorem. So in the setting where there are several mutually independent random variable, and those random variable determine certain number. So depending on this mutually independent random variable, we get some certain parameter, and then we want to show that that parameter is concentrated, so it's close to its expectation. And if that parameter, depending on this mutually independent random variable, satisfy this Lipschitz condition, that this mutually independent random variable have this gradation, and in this gradation, so this is a collection of mutually independent random variable. In this gradation, if you consider them, and it satisfies this Lipschitz condition. So all the mutually random variable, its outcomes are all same except on this part. It only differs on here. Then the value of this parameter that we are interested in does not change much. This is a Lipschitz condition, and the theorem says that if we have such a setting, then if this Lipschitz condition is strong enough, then we can prove this this concentration result. So that's what we have proved. So as this setup covers quite a lot, so this is, the setup that we mostly use. So let's consider some example of how we can use this theorem to prove some other things that we are interested in. So let's say G be a function from bracket n to bracket n, chosen uniformly at random among all n to the n possible functions. So there are n to the n many functions from bracket n to bracket n, and you choose one of them uniformly at random. So for each one of them, the probability that you pick them is 1 over n to the n. Then now we let L of G be the values which is not hit by this G. So you consider the image, and then you this is exactly the number of I, such that there are no J such that Gj is I. So here, this choice of G is, this is some probability space, and that probability space is actually same with the following. You consider, say, X, what letter do we have to use? X, I, let's not do this. So let's say G1 and G2 and Gn are random variable, so that the Gi is chosen from 1 to n in a uniformly at random. Then if you the plus independently, meaning that the choice of this and choice of this are independent. Then we have this n random variable, and with this choice, this yields a probability which is same with the above choice. So we have n mutually independent random variable, and which takes one of these finitely many values, and we consider the gradation. So let's say B0 is empty set, and B1 is just a set consisting 1, and so on to Pn, where Pi is just the first I integers. And we correspond this I with G of I, this random variable. Then this gives us a gradation. And when we consider L of G and L of G prime, we know that this differs by m-1 if G is same with G prime, or let's write it this way. G of I is same with G prime of I, or I in here possibly except one value. Then, from this definition, it is clear that by changing one value, the value of L can either stay same or increase by 1 or decrease by 1. So this satisfies one Lipschitz condition. Then we can use this theorem to show that this LG is actually concentrated around its expectation. What is the expectation? So expectation of LG, it's not difficult to actually show that by using linearity of expectation. This is n times 1 minus 1 over n to the n. So, so this, because for each I inside of n, we can actually compute the probability that it's never hit by any j, which is this. Then there are n of them, so you use linearity of expectation to add them. Then this is what you get. This is roughly like n over e. When n, supposing n is large, then this is roughly that. And we can actually now use this theorem. Then, we can just say, if we say it's just azimuth inequality, then depending on the setup, we might just say that it could mean this. Then we can actually show that the probability that LG is, let's write if it is the probability that it's deviated too much from here, we add 1 because, technically, we can actually show that this is either, deviate by plus minus 1 over here. Let's write it this way, plus minus 1. Then, this is off from the expectation by 1, so we add 1 here. And then this is our lambda here, and we apply here with all the CI1. Then we can actually show that the probability that it deviates from the expectation by square root of, n times some lambda is smaller than 2 times e to the negative lambda square over 2. So we get this tight concentration. So it's, it means that if we take, say, lambda as some function goes to 0, some function goes to infinity, say, some log n, then the probability that it's the L of G is more or less n over e plus, this is lower order term. This is linear term, and this is much smaller than linear term. This holds with probability, say 2 times e to d. So at least 1 minus 2 times e to the negative log square over 2. And this is something goes to 0. And you can also, take other lambda depending on your purpose. How sharp bound do you want? Depending on how sharp bound you want, you can also change that to get a concentration that you want. So this was a easy example. And then let's consider a bit more complicated one. So we first consider what would be the Clique number of given random graph. So let's consider random graph g and half. And we want to talk something about, let's say g is drawn from g and half. And what would be the Clique number of g? So this indicates this omega of g indicates the largest, size of the largest clique in our graph G. And we will show that in a random graph with high probability, its clique number is, we can actually, estimate its clique number. And then using that, we can also, show that we will also show that we can estimate the chromatic number of this random graph in a pretty good way. So now we want to consider, say, Clique number and chromatic number. So we consider this random graph, G and half. So you have n vertices, and for every pair you flip a coin. If this is head, you add an edge. If this is tail, you don't add an edge. And you consider this coin to be fair, and then it's independent. All the coin flip over pairs are independent. And now we want to consider the Clique number of this graph. Of course, every time you get this procedure, you might get a different graph with a different Clique number. But we want to show that with high probability, we can actually say something about this Clique number. So let's say fx is n choose x times 2 to the minus x choose 2. So what's this? So this is expected number of x clique in G and half. So we want to choose x vertices. Then this is number of ways to choose x vertices. And you have x vertices, then the number of pairs between them is x choose 2. And this is the probability that all of them becomes an edge, which yields a clique of size x. So this is the expected number of x cliques. And let k0 be the number satisfying fk0 minus 1 is bigger than 1, but fk0 is smaller than 1. If you consider this function, when x is 1, this is just n. When x is 2, this is n squared. N squared times half times n squared. No. It's roughly n squared over 4. Yep. So as x goes increase, it keeps decrease. And at certain point, it becomes smaller than 1. Before it was bigger than 1, but it becomes smaller than 1. And let's say k is k0 minus 4. So we want to now show that this, Clique number is quite concentrated on the, wait a moment. Let me change this a bit. So we want to show that the following theorem. So there is this constant C with the following, that the probability that this Clique number being smaller than k is very unlikely. So we want to show that we can find the Clique of size, at least k, with a high probability. Yep. So that's our purpose. And what we know here is k is 2 plus little of 1 log 2n, because this is, so for k0, this is roughly, 1. More or less. So from this, you can actually, show that one of those two, either this is bigger than 1 over n or this is smaller than n. From that, this must lie, for this must lie between 1 and 1 over n. Then from that, you can actually make the computation that the k0 is roughly this, and the difference between k0 and k is just 4, so you can write it this way, where this negative 4 is observed in here. And with this choice, we can actually check that this k is actually bigger than n to the 3 plus real of 1. So these are both inequality. So let's just put equality here because that's not so important. And as we know how it changes, so we can actually, this is bigger than 1, and if you move 3 more times to a smaller number, then it increases, and the increment is at least n to the 3 plus some little 1 term. So this is something we know. And then here we want to show that with high probability, we can actually find Clique of size k. So as I mentioned before, this is expected number of Clique of size k. And we know that this expectation is bigger than n to the 3. So if you just directly use Markov inequality, then, with the probability at least 1 minus 1 over n to the 3 plus little 1, you can see at least one copy of clique of size k. So you can actually prove that, I mean, this probability is big smaller than 1 over n cube. So that's easy from just simple Markov inequality, I mean, simple application of Markov inequality. But here we want to get a stronger, I mean, expectation, stronger concentration. So we want to use Azuma's inequality. But if you directly consider this Clique number, then this Clique number has expectation roughly log n. Like here, k is, I mean, order of log n. Then if you apply Azuma's inequality with the previous setup, then we can actually prove that this probability that the omega of g is deviate from its expectation by more than lambda is something like 2 times exponential of minus lambda square over, I mean, you have to get some c sub I square, whatever that is. So best you can hope for is that, I mean, from here, and we want to make sure that this lambda is at most epsilon times, say, log n. We want to kind of concentrate it in around the expectation. So this is epsilon times expectation. Then what you get here is, at best case, what you get is e to the negative epsilon log square n. Something like this. I mean, you have to divide it by some big number. But still, this number is much smaller than here. So this is roughly quadratic divided by log, but here we just have log, which is much smaller. So this is not good approach. This wouldn't yield what we want. So, I mean, as this is not strong enough, we have to do something a bit more. Some other parameter, some other random variable whose expectation is higher, but it's related to its Clique number, so that if you know some information about this new random variable, then we can also deduce the, I mean, information about Clique number. So we can consider the following random variable y. So when g is drawn from this random graph, so this is a random graph chosen according to the probability distribution of this random graph, then we let y of g be the maximum size of a family of H disjoint cliques of order k, size k. Then y actually will have a larger, I mean, expectation, and this smaller than k is equivalent to saying that y is 0. So it would have a quite large expectation, and then the probability that we want to measure is it's becomes 0, so which is kind of far from its expectation. So our intuition says that it might yield a better concentration result. So that's how we will prove this. We will prove that it has an expectation which is quite large, and from that we will use the Azuma's inequality. Again, I mean, this is determined by, so this probability space is a collection of random variables indicating whether H is there between these pairs or not. And for other pairs, I mean, you also have a bunch of different independent random variables. And those are mutually independent. And then once you change one of them, then this can change up to 1. Notice that we deliberately taking this as a maximum size of a family of edge disjoint cliques of size k. Because if you just consider the number of cliques of size k, then once you change one edge, then that can destroy or add many cliques of size k. So it's not Lipschitz with a small number at all in that case, but by taking this as a maximum size of a family of edge disjoint clique of size k, by changing one edge, it might add 1 or delete 1, but no more than that. So that's why we take edge disjoint cliques of size k, so that this becomes a Lipschitz parameter, as well as this can measure the event. This can detect the event that we want. So first, we prove that its expectation is bigger than or equal to this number. So we don't really have to find the exact expectation, as this lower bound is enough. We want to show that this is large so that it's unlikely to become 0. So let script k be the family of all k cliques of G. And let's say mu is the expected size of this script k. And it's not difficult to actually compute this, as you choose a set of size k, and then the probability that it becomes a k clique is this. So this is f of k, and we know this by our choice of k. This is at least n to the 3 plus 0, 1. And now we want to measure this y. And how do we want to measure y is that we consider, collection of cliques, and then we see how many of them are intersecting. And we have many cliques, and we will choose some of them, but not all of them. And then among the chosen one, if some of them are intersecting, then we will delete some. Then remaining ones form a disjoint clique. So this is kind of a alteration method. By doing that, we want to show that there exists, in expectation, there exists certain size of, family of edge disjoint cliques. For that, we define this expectation of size of this family K, and we let W be the number of unordered pair, say C1 and C2, of cliques of size K in G, which intersect. Here we are considering edge disjoint 1, so intersection meaning that they share at least one edge. They sharing vertex, we don't care. They share one edge, which happens when their intersection is at least 2, so strictly bigger than 1. Then what's the expectation of W? Is we consider all A and B, which are sets of size K in there, which intersect with more than one vertex. At least one edge. Then probability that A induces a clique of size K, and B induces a clique of size K at the same time. Then AB is counted in here. So we can rewrite this expectation in this way. Then actually this can be written as because all the things here are symmetric. So for fixed A, you can consider the summation here. So for example, you fix A first, then probability that the GA induces a clique, and we consider all the B which intersect with A at least one pair, then we consider this event. So conditioning on A induces a clique, we consider the probability that B also induces a clique of size K. Then this can be rewritten in this way. So here we multiply half because here we consider the unordered pair, but here because of load of A and B, it's counted twice when, one set is here and the other is there, or the other set is here and one set is here. And because all the situations are symmetric, this is same for any choice of A. And so this becomes all same. So let's say that's delta star, then this is half times summation of A, probability that it induces KK times delta star, and this part is same as the mu, which is the expected number of K cliques. So let's say that this is the definition of this delta star. And what's delta star? Delta star can be actually written in this way. So we fix A and we consider all the B. B, let's say A in intersection with B is I, then I is between 2 and K minus 1. Because if it's K, then A and B are identical, then that's not included in the W. And for given I, we count the number of sets B which intersect with A at I vertices. We choose I vertices in A, and we choose K minus I vertices outside. Then this together yields B. So this is the number of ways to choose B. And the probability, this conditional probability that B also induces a clique, is that assuming these are already edges, now we have to consider all the pairs here are all edges. Then the number of pairs that we take there is 2 to the, minus K choose 2 minus I choose 2. So I choose 2 pairs here are already picked as an edge in our conditioning. And rest of the number of edges here are this much. So we can write this as I choose 2 minus K choose 2. Let's say this as a G of I. No, sorry, not that as a G of I. Let's write in this way. We divide by n choose K and we multiply by n choose K times 2 to the minus K choose 2. So let's write it this way. And let's say this is G sub I. And this part is mu. So this is mu times G of I. Then if you just plug in the number, then you can actually show that G2 is more or less K to the 4 over n square. And Gk minus 1 is 2 plus little over n times Kn over mu 2 to the K. And because we know that K is roughly log n, and mu is here, which is bigger than n to the 3 plus little over 1. So we can actually show that this is smaller than G of 2. This is little of G of 2. And if you analyze this function, then we can actually with some computation, we can actually show that from G2, if you increase, then G3, its value drops. Here, if you consider, if you change I, then this part, as I increase, at first this part decrease. So this was roughly n minus k to the k minus I over some smaller value. But as I increase, the number of times you multiply n decrease. And these parts are kind of negligible at first. So every time it's roughly, decreased by multiplying 1 over n. This keep happen until I becomes quite close to log n. When I becomes quite close to log n, then every time I increase, how it increases from here to 2 to the I plus 1 choose 2. The increment here is roughly 2 to the I, which is in here becomes roughly n. So at that point, the decrement you get here is kind of divided by n, but here you multiply n, so it doesn't have to be necessarily decreasing. But so at quite a range, we don't know whether it increase or decrease. But after I getting bigger, then increment you get here is actually bigger than the decrement you get here. So it started to increase again. And it reaches g of k minus 1. And whatever happened here, it might increase or decrease, but we already know that it has been decreased so quite a lot. So even if here you increase a lot, the increment is not so big. So you can actually check that the values here are much smaller than G2. And because of this decrement and increment, and you just check that this number is much smaller than G2. So you can actually check that all these numbers are much smaller than G2. And then by this logic, so every time you roughly divide it by n, so these values are all much smaller than G2. So what we can check is that the G3, G4, Gk minus 1, all of them are small. So we can actually check that if you let I run from 3 to k minus 1, even if you add them together, it's smaller than G2. Then what you get is, so this expectation of W, which is half times mu times delta square, which is half times mu square times summation of gi, I equal 2 to k minus 1. And this is nothing but almost G2. So this is actually 1 plus root of 1 times mu square k to the 4 over 2 n square. Because G2 is this, you just plug that in. And then rest of the terms are smaller all the time. So you get this. So now you have this. Now we will use alteration method as mentioned before. So for each C, click in this capital K. We choose it. Let's say add it to this calligraphic C independently at random with, say, probability Q, which we will determine later. Then let W prime be the number of unordered pair C1 and C2, which are both chosen, with them intersecting at least one pair, one edge. Then the expected size of this number w prime is q squared times expected size of w, which is 1 plus root of 1 mu square k4 q square over n square. So here you just multiply q square because the probability that both of them are chosen is q square. So this is just like the alteration method. So what this says is if we delete one set of each such pair, C1 and C2, from this calligraphic C to obtain a, say, set C star of H disjoint K cliques in G, then what we have is, by definition, Y is the size of maximum H disjoint collection of K clique, and this C star is not necessarily maximum, but one such collection of H disjoint K cliques. So we get this inequality, and then from our construction, this has size. The expected size of C star is expected size of C minus expected number of W prime, which is, again, this is mu Q, because this is chosen from mu many. So expected size of K is mu, and for each of them, you choose it with probability Q. So at the last, the expected size of this is mu Q. And expected size of this is this. But if we let Q be n squared over mu K4, then this is twice of this, so you can actually get n squared over 2k to the 4. So which shows the lower bound as we wanted. So now we have this. So now we are almost done. So we enumerate E1 to EM with, say, M and choose 2. Enumerate the, say, pairs in bracket and choose 2 into this. And let's say BI is collection of edges from E1 to EI. This gives us a gradation PM. So B1 to BM. Then, it's easy to check that this satisfies Lipschitz condition. Relative to this gradation. Because if we change one of these EI, then the value of Y changes at most 1. So now we can use the Azuma's inequality as the Clique number smaller than K is same as probability that Y is 0, which has a upper bound as the probability that Y actually deviate from this its expectation by at least its expectation, which is 2 times e to the minus expectation of Y squared over 2 times n choose 2. So this below is that this is Lipschitz, meaning one Lipschitz. So you have to sum this and each CI is 1, and then how many you have to sum is 1 to m. So this is what you get. And what was the expectation? Expectation was n squared over 2k4. So if you plug that in, then this is e to the some constant times n squared over k to the 4, but k is k to the 8, but you know that k is roughly 2 times log n. So you get this upper bound on the probability. So this shows lower bound on the Clique number with a high probability. So we show that with high probability at least 1 minus this, we know that the Clique number of G is at least k. So now we will use this to show that the chromatic number of G is always, almost always, with high probability, chromatic number of G, when G is drawn from a random graph, is n over 2 times log sub 2 of n. So that's what we will do in the next time.